And well, thanks and thank you very much for the invitation, actually, to have the opportunity to come here to this wonderful place and tell you a little bit of the kind of the secret sauce that I believe. So please, when you leave the room, don't tell other people about it. The secret sauce that has been underlying much of my work in the last 15 years, I would say. I basically only discovered that I was using it myself as I was working on certain problems. So I'll try to give a little bit and exploit the idea that, we have a keynote here, so I don't have to actually just rush into the first three theorems and first five benchmark results, which will be impressive, but usually don't say so much. So I'll give you a little bit of an idea of what's going on and give you basically a recipe for doing things. And so I called it mining algebra, mining as in Bitcoin mining. Yes. So how do we reach into this deep body of classical algebra? So look at your textbooks on your shelf, or it probably has some kind of algebra books, from linear algebra to a little bit advanced, and maybe some category theory, and another kind of universal or non-universal algebra. And for power, which means for expressive power. So let's make this, wow, expressive power, but not just for power because it's nice and has very expensive words, but actually get to high performance, very good computation performance that runs well in practice. So I'll give you one example of that and indicate there's other ones on the way that have been done. And as I said, I'm advisor for a couple of companies now, mostly startup companies. But if you're in the game for another startup, I am. So okay. Okay. Yeah. So for some reason, it should work. So algebra. So what? Okay. So. It's algebra is used in a very you have to first talk to people, figure out in which sense, actually a very precise sense, they use the word algebra. So let's get a little bit close to this one. So usually, if you think about high school, and much of what you'll see later looks actually sort of familiar. It's just like using more expensive symbols, but it's like high school algebra. You have something with a plus and a minus and times, and once in a while a division shows up, but not so often. Okay, so. And that's formulas, and you're doing some kind of equivalences. You're rewriting them one into the other. And so a K-algebra, sometimes called associative K-algebra or commutative K-algebra or non-associative K-algebra, that's actually that's a class of mathematical structures. They're essentially rings. Remember what the rings are, with compatible scalar multiplication. Okay, so it just means that compatible means that scalar multiplication and the ring multiplication, they play nice, they're associated. Or where the K thing is usually, mathematicians still always use a powerful thing like a field, field like not even the rational numbers. They work with reals and complex numbers and algebraic numbers and so on. But if we're a kind of computer scientists, we're actually very happy sometimes to have some less powerful base structures. So you might just have commutative rings, and even semi-rings. So whenever you hear semi, you're talking to a computer scientist. So, and equivalently, these can be also written, described as K modules. So module is basically a vector space. It's just that the K thing here is not necessarily a field. It just has to be a ring, usually a commutative ring. And then you say like, oh, okay, so that comes with the scalar multiplication. And then you say, oh, we'll need another product. That's the product then of the ring. So that's two views of the same thing, okay? So think of it as a vector space, and somebody tells you how to multiply vectors, okay? And that's usually called, it's very important, it's a bilinear product, okay? Which means that it's, whenever you hear product, it's an operation that says if you it's two arguments, take one argument and you vary the other one, that gives you a linear map, okay? You do the same thing with the second argument, vary the first one, gives you a linear map. So that's the definition of bilinear. And the way you see it's bilinear is by writing it, looking at it, it looks at it's a distributivity law. Okay. So then we can also sometimes work with Boolean algebras, which are basically lattices with complement. So the difference is that here you have a plus, and that one is not idempotent, but you have an additive inverse. And here you have an idempotent plus, usually written like some other symbol, disjunction or union or whatever. And it doesn't have an additive inverse. It can't have it because if you have both additive inverse and idempotence, there's only one structure that has that property, namely the trivial one, consisting of a single element. So in other words, if you go with this direction, especially when the semi shows up, you're basically giving up on directly using, the classical algebras that have basically ringlet structures. And more generally, it's usually an object in category with an endofunctor, which is a very complicated way of saying much more general. But the key thing is we have some observations. There's lots of situations where one has a structure with plus and some kind of bilinear operations. These are usually just the product on scalars, right? Multiply two things. But if you go up into more complicated, more compound data structures, you have the vector, the Schur product, you have the tensor product, you have the inner product or the dot product, you have the Cartry-Rao product. There's lots and lots and lots and lots of different products. They all are bilinear, okay? So which means like, oh, okay, they all fit this image of like, we have a lot of operations. There's a plus in there. The scale up multiplication, by the way, scale multiplication is also bilinear. So there's a lot of these things, and a lot of our programming turns out, that's the message here, is actually programming with constant functions, linear maps, I should say, or linear maps, and bilinear maps, okay? And so the observations are this, okay? So and there's a huge mathematical literature, linear algebra, multilinear, tensor algebra, with deep results, spectral theory, which just means like, wow, you can always kind of find a sort of normal form or property of these things. And so the temptation now is, what I'm suggesting is, look at those actually, books you have on your shelf, they might actually be 500 pages long, whatever, but, they might be actually filled with chock full of good ideas for high performance computing, okay, for great data structures. They're not in the books. You'll have to come up with them, okay? And the other thing I want to say is what I found to be very, very useful is resist the temptation to normalize, okay? So it's like, I have, a relation which is just a list or, a list of pairs. And then when I, take the Cartesian product of those, right, which turns out to be the tensor product here. And then you say like, what is that? Well, you just enumerate, all the pairs from this one with all the pairs of this one. Basically, you're multiplying out this distributivity, okay? Don't do that, okay? So it's like, do less and you'll get more, okay? So that's basically the message I'd like to give you, and I'll give you a couple of ideas. So what's the idea? It's like you take your data, you have actually relations or patient records or whatever. You say, model them as rich algebras with their inequalities. By rich algebras, means like the algebras that are in your book. They might be tensor algebras and with a number of products, and but they're just think of them as like as an abstract data type, right? Because they have qualities that are exploitable, and the exploitation consists of, look at the equational properties for efficient data structures and algorithms. Very often they have universally quantified, this expression is equal to that expression, okay? And you can say, wait a minute, I can do this at runtime. If I have a term representing my data that looks like the left, and I have a very fast pattern match, then I can rewrite it into the right-hand side and continue computing there. This makes it possible to use the context of a call, what you do with some values, to determine, I'm going to use another way of evaluating my queries. It's like a generalized lazy valuation. It's because it's not just lazy. And then at the end, I found it to be useful to shake off all the algebraic generalization and and explain in terms of original data model. Because many of these things were rejected because we started with things like let R be a K algebra, and then even database theoreticians were kind of like, oh, I'm not going to read that. Okay, so you just have to kind of pull back. So in other words, when you read it, you won't find the algebra in there, okay? But it was there in the process. I'll show you 2 case studies. Actually, I'll only show you 1 case study, which is a combined case study. And actually, this is ongoing research. And it's based on, so this is actually based on the recognition of the last 15 years that domain-specific languages and the data structures and algorithms I was working with in various different domains, contract specification language, for example, for distributed ledger technologies, that's digital startup that I co-founded, is basically I was doing these things, recognizing, wow, there's all these qualities that are wonderful exploit, but they all look so familiar. Okay, they look so familiar until I realized one morning I woke up and I said, wow, that's because you're doing abstract infinite dimensional linear algebra, right? So the thing I hadn't recognized there is because I'm a poor person who studied linear algebra at technical university. So at technical university, linear algebra was something about matrices, okay? But that's not linear algebra, okay? So that's just a representation theory for finite dimensional linear. So I can do it. So ooh, okay, that's interesting. Let's work with it. So there's a couple of papers you can look at. Backgrounds, some of them are actually ongoing. I didn't mention actually, Bob 2026. So I think there is a person, my slides are there. You can look at some more of those things.
Video too.
Pardon? And a video. So so this one is, that was tuned more to, people who say like, stop, stuff about algebra stuff, show me how it works, and so I can program it and make sure it runs fast. So this is FLOPS. So it's functional logic. Okay, so I'll come to the functional later, but let's start with the logic. So querying, is sometimes called, that's just a processing of something. What you specify is usually a subset, but I'll introduce the full thing of relational first order logic. Now, who remembers, who's taken a logic course actually? Just first order logic, predicate logic. Okay, all right. Yes, that's good. Okay, that's really good because to you this will look, yeah, why don't the database people use that? Well, don't ask me. Okay, so it's because it is used, but then sometimes use their own terminology. So I'll use standard, what is textbook logic terminology. So what is a formula? So in other words, querying is basically, the thing is like, I give you a formula. First order formula, what is first order? It's just built from and, or, not, implies, exists, and for all. Okay. All right. Just what you've seen before. But it will usually have free variables in it. So the free variables are the ones that say like, wow, and I want to collect all the tuples x1 through xk that satisfy this phi. To be precise, that satisfies phi in a particular model. And the particular model means like, what's a model? It means like every predicate symbol that occurs in there is interpreted as a relation, which means a set of tuples. Okay, let's agree on that. Relation is a set of tuples. I didn't say anything about finite here, right? That's very intentional. Any set of tuples, okay. So there has been traditionally since the 70s breakthrough abstraction work by Kahn, people in the late 70s developing things that's saying like, well, we want to work with finite relations. Because finite relations is something, we call it a table, right? And you just have the tuples listed in some order. And how do you write an infinite relation? So let's forget about those finite relations, okay? And then you say like, okay, these are the finite relations are the ones that I use in the formula, right? But then the phi here, as we've seen in earlier, Monday, the phi here might not be safe, right? So safe here means is if the query output is, so basically we call a phi here, we call that one of the whole query actually with the x1 to xk, we call it safe if we can guarantee that the output, the set of tuples satisfying phi, is finite whenever all the input relations are finite. Okay, so another term would be finiteness preserving. Okay, and as I said, here's some more examples that you've seen. Some of these queries are not safe. I mean, all these are not safe, right? So you just, this is a finite relation P, but the output, all the x's that are not in P. Okay, so let's assume the underlying universe. So think of the attributes. It's very important without loss of, it's infinite, right? It's all the strings in the world, okay? They're not in the strings in the world, all the mathematically conceivable strings, which is a lot more, they're infinite, okay? So yeah, so if this is a finite number of, this is a finite set of strings, then this is the complement of the finite set of strings. That's certainly an infinite set of strings, right? So that's not safe. This one is that, so it's like all the strings that are either in P or in Q. And that's the pairs of those. But as you've seen before, that will also in general be unsafe. So infinite one, because it says like here it says it's if you're in Q in X in here, then you can pair it up with all kinds of Y's, right? And just this one here, right? And then you just get a union of another infinite set. And so even this one is actually quite tricky. Look at this one. This looks like so-called joint query. It's just a conjunct of two things. But what? Wait a minute. Look over here. X, Y, Z are the three variables here. And I'm saying give me all the four tuples. X, Y, Z, U. All right. So the set of X, Y, Z that satisfy this are finite. But I'm asking for the set of all X, Y, Z, U. Well, there's any U you can put in there, any string, right? So that's an infinite set again. And this one is, whoa, negation is, you can see that's tough. And then, if quantification. So after a while, you find out, oh, so safety in general is undecidable. So I give you an arbitrary formula, is it safe or not? So the main relational calculus from 1978 or something like this is, it has syntactic safety restrictions. Let's say I'll give you basically inference rules or some kind of algorithm for saying yes or no to being to be safe. And it's a sound system in the sense that if it says yes, I'm safe, then the query is safe. But it might also say sometimes I don't know, or you're not safe. The query might still be safe. Okay, so remember, it's a sound approximation of this property. But it has a very important property, namely, it is co-expressive of causal relational algebra. That's the classical relation. So everything you can write down with relational algebra expressions, you can write down with syntactically safe calculus expressions. Sorry for the long introduction, but just also set the stage here. It's not trivial to have these kind of safety things. So let's look at this one. So this is called the kind of range restricted safe range formalization. Okay, as I mentioned, there's about four others. There's the RRDI, NRD, AD formulations. They all prove to be co-expressive equivalent. So this is one spec. It has to do with what we saw on Monday, basically saying like you want to find out the variables, are they covered? Okay. By conjunctions, one of them is covering is enough. For disjunctions, you have to cover both of them. The coverage is basically a way of saying like yeah, that's the coverage notion. And this one. All right. So let's look at this now in a small subset first, and say a conjunctive query is a query where phi is built only from atomic predicates, conjunction, and existential quantifiers. Okay, nothing else. No negation, no fraud. Okay. And importantly, the free variables have to be exactly, as you saw before, have to be exactly the free variables. So So the set of x1 through xk, tuples I'm interested in, have to be exactly the free variables that occur in there. Okay. Remember this case where I had an extra free variables and all of a sudden the whole thing was infinite. So in a joint query, it's just a conjunctive query without quantifiers, and conjunctive query is the same. So once we're in this one, we don't have to check anything, because if you give me finite relations and I take a query of that, I get a finite relation out of this. If you have questions at any time, you just blurb. So let's look at some examples. And these are not accidental. Especially this one here. It's like a database engineer's nightmare. So that's the essence of it. So it's just here's like you can see it's a joint query, right? So it's all the x1, x2, x3, all the triples, all the node paths where x1, x2 occurs. Think of this as a graph, right? Where x1, x2 is in the edges. Next one, x3 is in the edges. So it's just the node path of length. Yeah, edge length 2 or node length 3, whatever you want to call that. So I'll count the nodes here, 3. But I say width. I'm not interested in just the triples. I want to make sure I'm interested in the nodes where the last one points back to the original one. So this is a triangle. If you draw it, you can see that it's the edges form a triangle. Okay. So it's the same as here, x1, x2, x2, x3, and now we conjoin it with conjunctively with x3 pointing back to x1. Okay, right? So it's easy to formulate this in SQL query because that's basically relational algebra. It's certainly always safe. And this would be a canonical way of saying it. So it's basically the SQL way of writing this down is saying, selecting all the, first components of R. So R1, R2, R3 are the same here, such that the second component of R points to the first component of R. Then in the, triples actually, I should have written as x1, x2, x3. So it's triples here, right? So that the second one, as I said, it's just basically expressing this. Okay. All right, you're with me still, I hope. So let's do this naively. We'll get to this point, actually. Is it really naive? Well, look at this, I mean, you probably did this you're from Japan, so you did this probably in high school or before high school, right? So, so it's, what is, the set of all triples here that satisfy conjunctive property. That's the intersection of those triples, right? Are we agreeing? No? All right. So let's just write it as saying that it's, well, conjunction here. It's all the x1, x2, x3 that satisfy this property. x1, x2 is in R. x1, x2, x3, and x1, x2, x3. Is that wonderful? Now we only have to implement intersection, right? Well, look at this one. Is anybody worried now?
Sounds safe.
Sounds safe. I've taken a safe query and decomposed into 3 unsafe queries. Like, you can't do that, right? Well, we'll do it anyway. But because it's, let's think about it. Said theoretically, it's certainly correct, right? So I'll just put this into your head. All this safety thing is it's really necessary. So we'll do this. And so what? Can we maybe represent these infinite relations finitely? And not only represent them finite, but then also process, with union and intersection, process them effectively and efficiently, even though they're infinite. Okay. Now, as a function programmer would say, actually, I've seen a lambda before, right? So if you write lambda x dot x, if you think about it, a database person would say, oh, that's not a table, right? Because that's infinite, right? Every string is mapped to every string. You get basically a list of an infinite set of strings. That's forbidden. Okay. But we're not scared of actually representing finitely infinite things, right? Oh, let's just do this here too. All right, so okay, so let's shift perspective a little bit to see that this is actually not that hard or that difficult, or even, once you've seen it, you will say like, of course. In fact, if I'm lucky, after 31 slides, you will say, of course. But that just means that you didn't say in advance. And that would be a great achievement, I think, for me as speaker. So let's look at a finite K array, in this case, a binary relation, okay? So this is a binary relation, it has 2 tuples in it, 4, 8, and 2, 19. This is usually how we also write it down, right? So it's like, a set, and we process it as a sequence of pairs, right? What is the tensor term? Let's start with that one. The tensor term in the setting is a finite set union of Cartesian products of subsets of U. So remember, U was our infinite set of attribute values. So think, whenever I say U, think strings, okay? So it can be written, every finite relation can be written canonically in the following way as a tensor term. Namely, a pair is nothing else but the singleton pair union that singleton pair. And a singleton pair is nothing else but the Cartesian product of singletons. Okay. So it is the singleton set 4, Cartesian product of singleton set 8, singleton set 2, Cartesian product of singleton set 19. All right. What have we won? Okay, I want to indicate something right away. We've won something, namely, we have an enormous variety of different representations of the same set. And that's a win. For example, if somebody says, I want to represent the, this relation is the Cartesian product. Remember I said the Cartesian product of this finite set with that finite set. And you multiply it out, you get m times n pairs, right? So you have m here and n there. But if you just write it down as like, excuse me, I'll write the set here, that's a set of m elements, and then put a cross. This is really a symbolic Cartesian product operator. I'll put it there. And then the other one, it's m plus n, okay? And so think about it, is that, oh man, but you have to multiply that anyway afterward. Well, really? Imagine somebody's interested in the cardinality of that set. They will say, oh, this is wonderful homomorphism that says the cardinality of a Cartesian product is the cardinality of the left times, as a scalar, the cardinality of the right. You never multiplied it out. You computed cardinality in m plus n time, even though the cardinality is quadratic. It's m times n. I'm not going to, but so keep the first thing in mind, okay? This is just already an advantage. But here we get to the second advantage. It says like, what if I want to represent this nasty thing? Remember? There's like, instead of all x, y, there are r. Sorry. But I have this extra x in front here, okay? That's infinite, right? Okay? So imagine now this is the r here. So how can I represent it? Well, we have tensor terms. So we'll just write it down as, this is the 4, 8. And then say on the left, we Cartesian product it with the entire universe. All right, the entire universe. And the same thing over here. Okay, as you can see, this is a tensor term. And you will admit it's a very small tensor term, right? For a very big relation. Okay, cardinality-wise. So let's define now the notion of finitary relations. Not all relations can be written down like this. You come up with all kinds of crazy relations, but or not so crazy relations. But let's just say all the relations, they're denotable, expressed by a term. And remember, terms just a finite union of tensor products, okay? Where the subsets of U that are occurring there are either finite, so we have something like this, or cofinite, which means like this is cofinite because it says like how many elements are missing to get all the way up to U. Well, in this case, the empty set. So the empty set is clearly finite. But in general, you could say, well, this is maybe a smaller set, namely set U minus 358. Okay, well, that's a cofinite set because 358 is a finite set. So okay, so you're with me on cofinite and finite, okay? Pardon? Yes, cofinite means that inside of the universe, right? So I give you a set. So you have the set of all strings, okay? So if I enumerate a finite number of strings, Alice, Bob, and Charlie, finite. But if I say it's all the strings except Alice, Bob, and Charlie, except a finite set, okay? So then we call that a cofinite set. So a set that is neither finite nor cofinite is the one that has all the strings that are uppercase. All right, that's not finite. There's infinity of them. And the remaining strings is also infinity. Okay. All right. Is that because it's important you grab this? Okay. So the intuition here is like, wait a minute. Then I can write this down as the empty set with a tag that says, remember, it's the complement of the empty set. Complement means like means in this given universe. Okay. So all of a sudden we have basically a representation of these relations that are basically all finite. So that's the reason why I ended up, we ended up calling it finitary. I would call it like finite enough. Okay. All right. Because you can write them down as a finite tensor term like this with either cofinite or finite subsets. Okay. So let's then define finite relations. The relations in all tensor term, the subsets of U are either finite or cofinite. So R prime is clearly finitary since U is cofinite. So you could say like, well, maybe we can actually do this intersection thing, remember? Because all the relations now are not finite anymore. They're all finitary. Actually, from here to get a very fast solution, you'll be surprised. It's very short. Okay, so the next thing is like we need to do an intersection. You see that? We need to do an intersection. Yeah. And so the idea is like, which means that if you want to find a triple, okay, so think about it. There's like there's a bunch of triples here, bunch of triples here, bunch of triples there. But when you do the pairwise, or we'll do a k-array intersection, we'll have to find all the values where the first, let's start with the first one. Well, the first value is the same. That's what it says, right? So we have to get a very efficient way of representing this binary relation such that we can very quickly find out if we have an element that occurs anywhere here as first component, which are the other tuples over here that also have the same value. Okay. So here's the next trick, you could say, is that it's not written up. This is, it's just a recent result. Actually, it's an Airport Copenhagen result on the way here. So, yeah, sorry.
I don't mean to interrupt you, but so you can define things that are finite or cofinite, and those can represent the query that you're interested in. But wouldn't it also be fine?
These are also infinite relations.
Yeah. If it was finite or universal.
That's a finite or universal. That's yeah. That's a finitary relation.
You know what I mean is, wouldn't that also suffice to express the query you're interested in?
In this case, yes. Yeah, absolutely. But as a clue, of course, later on we'll just throw the joins away and all safety away and do this for all of the relational calculus. Okay. So so yeah, you're right. Absolutely. You could restrict it in this case where you say like it's exactly this insight is that yeah. Keep that in mind. Okay, then maybe you can explain what's going on here. So so the computing intersection efficiently requires finding the same attribute values in one relation in the other relation. By finding, I don't mean very slowly iterating over them. Then you're, it's in the end, remember, it's all about performance. Okay. So we want to make sure that this is done as quickly as possible. We need to have a very efficient lookup to get from an element in one of those relations to all the relevant tuples in the other ones in constant time, basically. Okay. So the intermediate step, this is the mathematical way of putting it, is like, well, we know what a characteristic function is, right? So if I give you a set, then the corresponding, characterizing, as we can call it, characteristic function, is the function that maps every tuple in the universe, in this into either true if it's in the set, and false if the value is not. You can curry this. That's very important. So there's a curry characteristic function that it has this form. There's like KUs here. And at the end, we get either true or false. And we say that it's a curry characteristic function of a given k-array relation if the following property holds true. This is the characteristic function property, just curried. Okay. All right. Characteristic function, is that still something people talk about, or I hope so. Okay. So it says like a function, you give me x1 for xk, and I'll give you true if and only if the tuple x1 for xk is in the R. So let's define now the notion of a finitary function. It's basically all the current characteristic functions of finitary relations. Okay. Yeah, and so this is the key theorem. It turns out the finitary functions can be written as nested dictionaries. And by dictionaries, I mean what people in the Python world or in some data structure world call just ordinary dictionaries with a tip. They're not equipped with points, but they're equipped with programmable default values, you could say. So so generalized points, you could say. So let's go and see how what I call simple join is, because it's a simplified version of a very famous algorithm called generic join. It's worst case optimal, and I'll expand on that when somebody wants to ask them, because there's a whole proving that stuff is a whole separate story. But it has the following ingredients. So think of it as a program. You require nested dictionaries with constant time length, which means, like, you ask the dictionary, how many keys do you have? It says in constant time 5,500. Okay. Then it has constant time per element iteration. So it says, like, please iterate through all your keys, and it will do that in O of k time, right, with the number of keys. Then it has lookup in constant time or in quasi-constant. So just to give you an arbitrary value, whether it's in there or not. And it either says, here's the associated value. All right. So the associated value is not just bool or whatever, but because here, this is a dictionary. Then you give it a value, and if it's in the domain, so if it's in the keys, and the domain being in the domain is like exists some continuation tuple here that gives you true. So if it's in there, then it returns the curry function, right? All right, and the curry function, that's dictionary again with the same properties. So then you say you always iterate over the smallest set when intersecting sets. So when you have the domain of a key, this is basically the key thing to keep in mind. You don't do that, your performance will quadratically blow up. Okay, asymptotic blow up. So whenever you have, like, I have this set of keys here in my set, or it's just a set of elements, which is the same thing as a mapping from keys to true false. And here's another one. You basically say, I need to intersect them. You first go ahead and ask each one of them and say, how big is your key set? Right? Dynamically. And that's the reason why you need the answer in constant time. Then you choose one of the intersections. So remember, there's 3 of them here. We intersect all 3 of them in one go. And we ask these 3 and say, which one has the smallest? Oh, they're different. Which one has the smallest? This one has an infinite one that's huge. So we ask these 2 in reality, which one has the smallest number of associated values on the row? All right. And that one we use to iterate over. And for all the other ones, do a lookup. All right. Remember, that's constant time. And the last thing is, like, this iteration of variables in the query in any order. That means, like, it's basically, you got to read this as iterate over all the x's you find for each one of those, iterate over all the x2s you find that are associated with something, and for each of those, iterate over all the 3 ones. Sounds very simple. And it is simple. So, so there is a proof of optimality, worst case optimality. It's constructed in general. It works. And I have to mention this because it took us years to get that one. There's an independent proof of this one. Is an amortized complex analysis for allocating each constant time computation that is occurred here, a constant fraction of outputs eventually produced, but it's outputs that actually arise from input padding. So we add ghost data, attach computation steps to. I don't know. So that was it took us a while to do this one. So in this case, we can prove that actually this algorithm, when it executes, will execute asymptotically as fast as is presently known. There's still open problems about linearity. So real optimality, but that's it. Shaking your head. Sorry.
For cases, there's no algorithm. You got it. There's also notice that I don't buy comments that if you have no certain degree constraints in data, for example, functional dependencies, you can do better with this assumption. Anyway, there's vast literature here, which I know only a fraction.
Yes, so I know also fractional. This is about generic algorithms, so right. So it has to work for all queries, right? So it's generic, and so it doesn't have any restrictions. But the key thing here is that as far as I know, it's still open whether for the general class of cyclic queries there exists really worst case optimal. What that even means, I mean, optimal in the size of the output results for so-called acyclic queries. So that's why I emphasize the first one was kind of in other words, intuition here is this is actually easy in a way, but it's not really easy because you get this can have huge outputs. Okay, this can be quadratically many of these edges. Yeah, can be quadratically many of the edges coming out here. But this one always is bounded to have maximum into the 3/2 output. So the last step basically throws, in some cases, almost all edges away. And that's inherently so. And so the worst case outcome says like you get only as much time as the maximum output you have. And so in this case, since the maximum output is smaller, we don't call it optimal. Sorry, if you compute by first doing the filter part and then filtering away. It's kind of a tricky thing, but in practice, actually, you want things to run as fast as possible in terms of the size of the input, really, and render in some output. Yeah, let's just look at this. So now we can turn this into code. It turns out actually Python is a really great language for this because it's built-in dictionary. So built-in, there's no extra libraries used here. The built-in dictionary has exactly the right performance characteristics. Remember constant time, like really, you iterate over the keys in constant time per. You build also, very important to build actually a dictionary, a bulk build from a list of pairs, as in linear time. And very importantly, it has built in a field that says, I'll tell you how big the cardinality is. For example, int map and int set in Haskell and in standard ML don't have that, so you have to code it by yourself. And there's a couple, I think Scala has it also with built-in. But it's kind of funny that the dictionaries in Python had just out of the box the right performance as an asymptotic performance card. And look at the code here. So this is the triangles. So the first thing we do is we build this two-level dictionary. Remember, this was this really characteristic function, but that's what it is. And this is actually how we build it. This is just a constructor, which is 3 lines of code. I can show that too. Then we build up the result and say, all x in the smallest, that's very important, in the smallest set of R1 and R3. If you leave that out, you're not going to have much fun. We have to do dynamic. Then we go in and for each one of them, we go through all the y's. And the y's is actually, for all R1x. Remember the R1x had a y, right? On the right-hand side. But now we have, for the second R2, we have the keys. It's the x's on the left-hand side. We go through those and say, for the smallest of those, we check whether y is in R1x, because at this point, this is a set. Set is a map. Here's a map from keys to bools. So this is a way of actually checking that Boolean, right? And then we do for all the z in the smallest of R2y. Remember, there's a z over here. And then in R3 of x, sorry, this is the z here. No, this is y. So anyway, we get the clear. So we have to build 2 dictionaries, one of them in one direction, the other one's okay. And so it's completely systematically and simple-minded written down. This is a functional programming conference, so better also show you some Haskell code. So it's basically the same thing. Okay. All right.
So those keys, all don't actually give you all the keys, right?
It gives me all the keys as an iterator.
It doesn't. If you then call smallest point.
Yeah, but that's the same. Okay. The keys is a set, right? So they can tell me in constant time. Because here I'm iterating over, I don't know if I'm iterating over this one or that one.
Yeah.
But I have to get the answer that says like, how big are you, right, in constant. And then I use that one. Yeah, so x, I use that one to iterate over. Yeah.
Did you make it big? You make what do you change?
Dict2 is just a constructor because I have it basically is the fortunately wait, maybe I have it. Yeah, no, I don't have it. Sorry. Dict2 is one that builds a dictionary of For every A, it associates the set of associated values B in the input. Okay, so in this relation, okay. That's just the code they would write to build that dictionary up, because the dictionary goes from A to a set. And a set is a special data type, which is just really just another map, a dictionary, but okay. So we're just building this up. So whenever you see, if you go through, in this case it's BA, but if you go through a pair, you say like, oh, as an A and as a B, have I ever seen an A? If I haven't seen an A, then I better make sure that the current associated, value for an A for that dictionary is initialized to be the singleton set with the thing. And next time, if it's already there, which is it's already there as a key, then I'm adding it to the set. Just add the element to the set. I have the code here. It's another 10 lines, the whole thing, okay, of Python. Okay. Also, the smallest thing is just, check the length attribute of those two. Haskell, if we see it, but it's basically the same thing, but I like, you can see this, okay. So the Haskell was a very simple program, doesn't even run. So let me see. So let's look at some performance numbers. So, which you can't see. So I'll just point to a couple things. SQLite and DuckDB, they're in-process query engines, which means that basically libraries you can call on, and they will, take the data from the same process, which means like, you can basically share the data, and then have some, code for executing a query, an SQL query, and then returning a result in some fashion. So it's usually, in this case, I make sure that the thing is always materialized. So like you get a set or a sequence of pairs in, you get a sequence of triples back, materialized. DuckDB, that's state of the art, you could say, in terms of in-memory database. And then we have Postgres, MySQL, which you should recognize. Then Umbra, which is a research database, which is written extremely highly performant, and turns out the only one that actually implements these things, I think, in worst case optimal time of the database systems that are accessible. Kuju we tried, which they say they are there. We couldn't verify that. Data did say that. And then we have Chinese Simple, which is what I just showed you. That was the Python result. There's also this generic one. And then we have naive, just to indicate what happens if you just do this with nested, so without the smallest, without the associative access, you get cubic performance here. So this is a log print, okay? I couldn't show these data here in a linear thing because they would be like this and all of it, okay? Right, so log print, and then we have the Python version, then I had a auto-generated sort of like a C version, and also a Haskell version. Basically, the Haskell version is so important. Look at this, you can see that they are, except for Umbra in some cases, which is actually out of process, they're by far the fastest. What you've seen the code is by far the fastest you get from these engines. There's also, we've done experiments with about 10 in-memory, in-process language integrated query processors, and the story is about the same. So, because the thing is that this data set is truly nasty. This is one that kind of provokes this, we call the Alice data set. So it means like Alice is number 0, and then you have the numbers from 0 to n-1, and Alice likes everybody, and everybody likes Alice. Okay. So it's got 2n edges, right, for a given n, and this is the n here, you see. And it turns out, if you look at this one, the output is not n to the 3 halves in this case, which would be the maximum size of a triangle. It's actually linear, okay. And it turns out that this kind of linearity is being exploited by actually also Umbra and actually our algorithm. Okay. So it can run faster than the worst case optimal outputs if there's certain properties in the input. But just as you can see here, there's like this is cubic, quadratic, linear time. So you can see by parallelism that only these versions here, which are all from the Python version, they're linear plus. At some point, Umbra has started things. It's good, and then it just crashes because Umbra is amazingly fast, but uses a certain amount of memory. So it's an in-memory database system. And the other ones, they're kind of like hopeless because you can see that they grow roughly quadratically. Okay, so actually it turns out DuckDB does something strange, very interesting. It's a little bit faster than quadratic, and the other ones basically are quadratic. They basically compute P3 as I said before, and at the end they just throw most of the edges away. If you compute P3, remember there's quadratically many of those. If you look at AN, so of course you have to spend quadratically many steps to even get that set of triples. So the story is here, by actually in the intermediate steps having finitary relations, infinite relations, and using those and having data structures for those, we can get very simple code, and we can get we can explain why it runs, and we can even explain why it runs in worst case optimal time. Yes.
I'm somehow confused by your data set. Alice loves everybody.
And the
So
other.
I go from Alice to everybody, and then the only way I can go
Yeah.
never come back to Alice is directly to Alice. So
Yes.
there are no triangles, are there?
Yeah, Alice likes herself too. So yeah.
Ah,
Yeah. So and the interesting there is just like every start with triples, like anybody here goes to Alice, and it goes to anybody the quadratic many of those triples. Okay, that's all. Okay, so let's go beyond joint queries, and said I'll finish shortly. So we've seen we can compute with cofinite, finite, infinite relations. Okay, so these finite relations. So is safety even necessary for arbitrary queries? So now that we've lost our fear of finiteness preserving being holy, I mean compositionally holy, maybe I don't know. It turns out the theorem is that the smallest class of k-ary relations over an infinite U, that's defined by unrestricted relational form. First order logic, as you've seen in the beginning, are finitary relations. So no safety required. I'm not imposing anything at all. The proof is, well, we start with a Boolean algebra, then we know by Stone's set algebra, you get a set of fields, then we get a Boolean tensor algebra, which is an almost free Boolean algebra, then generated by all the subsets. Then a derivable Boolean tensor algebra equalities. We're using like, oh, okay, these qualities are certainly sound in there. Not all of them are required, actually. And then we use rewriting theory from the 90s. So path, recursive path ordering in this case, but just squinting at the operators and saying, oh, I can orient, actually, equalities are not accidental. I can orient the ones from left to right, and then I can study the normal forms. And the normal forms are tensor terms. So what that means then, given any tensor term as input, so not only finite relations, but also finitary relations as input, the output of any purely relational first order logically definable query is a tensor term again. End of proof. Okay. Proof is constructive, so the translation relational calculus to a finitary relational algebra is part of like, how do you generate the values, and that generalizes Cohen's relational algebra. Okay. And it has projections, and most importantly, it has an operator that says take the complement. It doesn't say take the complement with respect to which finite set. The complement. Okay. And which can be infinite, of course. So this rewriting can be implemented, we did it, and we can show that it's not efficient. Not surprisingly, okay, because it doesn't have an efficient associative access from one relation, we need an intersection, to the other relation. But wait, lo and behold, I just introduced one of those class of functions, namely the finitary functions, and they do have actually a nice data structure. So we have one of those, which corresponds exactly to finitary relations, so we can completely represent them. So, yes.
Why do you have to say the smallest class of k-ary relations? Like, are you simply saying first order logic can only define finitary relations? Is that what you're saying?
Yeah, unless you put in some other
Unless you
relations.
Put in a non-finite.
Yeah, that's what the smallest means. The smallest class is like you can't generate anything else, but planetary relations. It's just standard inductive, monotone description of Seigert's. Which relations can you define? And usually it's implicit. You say like, by putting, relational queries together and composing them, and then looking at all the relations you can construct this way, any finite way of doing this one. Okay. But you could take a least or a greatest fixed point operator on top of that, and then you get into the inductive or the data log world. Okay, and then it gets interesting again, of course. But this is just a way of saying you can't define anything else. The smallest class that contains the empty set, well, the empty set, because then it contains the universe, and also all singletons. Okay, I should have said that. Okay, so you just say let's assume all the single tuples should be in there. Okay, so then because the single tuples really generate the generators of this. I'm almost done. So well, the so part is like, whoa, this is exciting. Okay, so that's what we're working on, actually seeing how to work this out in practice. So we can now substitute. So this corresponds basically B algebras. It's basically a relation is a mapping of set of tuples to a Boolean, right? And the Boolean is in this case semi-ring. Okay, but you can put in other base structures. You can put in like another semi-ring, namely non-idempotent one, the initial non-idempotent one, which then you get multisets. If you put in something that like the integers in there, something we call polysets, which means like these are multisets including negative multiplicities. This another term for those is actually freely generated Z modules, because it's finite sets of these with multiplicities being from any integral number. You can also put in a provenance ring if you want, so the whole thing goes through. Even the computation, you put in real numbers, then you all of a sudden see that's basically the finite dimensional algebra of Hilbert spaces, or the real numbers, which is used in machine learning. Put in the complex numbers. This actually got into quantum computing. I realized that if you stick in the quantum, the complex numbers, then basically, the quantum, Hilbert spaces and so on, and quantum bits for all of this. So the idea is like interpret data in a richer domain for efficiency, pull back into original domain. So we've seen this queries, this automatic differentiation, incrementalization, also running queries backwards via symbolic variables. And you can do some of those other things. I don't even know what it means to run a query backwards exactly, but so we have more examples of this E method named differential programming with symbolic differentiation adjoints. I didn't get to this one, I promised in the abstract. Quantum circuit simulation via polyadic density compositions, same thing. And we also use this as the kind of the resource calculus. So that in this case, without the product operator, it's just the infinite dimensional linear algebra is the greenwashing proof tracking and tracing of energy sources, including trading of production certificates. Sounds very diverse, but the underlying actually theme has always been model things as an algebra, use its properties, and then apply it, and maybe take the algebra part out of when you publish this, take it out so people don't focus on the application. Thank you very much.